Welcome back. We ended the last video on a bit of a cliffhanger dealing with uniform distributions, so let's pick right up with that. So we were waiting in line at Burger House, and we wanted to know how likely we are to have to wait at least 3 minutes. And we'll revisit this again with a normal distribution where we have mean and standard deviation and a nice normal curve to play with. But for right now, all we've got is the assumption that every wait time is equally likely. We're just as likely to wait 2 seconds as 222 seconds. So how likely are to wait at least 3 minutes? Now, had this wait time range been between 0 seconds and 360 seconds, this would have been a no-brainer, right? That's 0 and 6 minutes. So to wait at least 3 minutes, well, that's half the time. We would have a 50% or zero point 0.5 probability of waiting at least 3 minutes. But it's not 360, it is 350. So how do we find the area now? Well, let me make my uniform distribution here. And I'll do this in minutes just to make my life a little easier. And you'll see here, I have some probability of waiting a minute or 2 minutes or 3 minutes or 4 minutes or anywhere in between. And that probability is the same all the way through and everywhere in between. And that's fine. That's what we expect. That's a uniform distribution in a nutshell. But how likely are we to wait at least 3 minutes? And again, had it been 6, we've been exactly halfway through, but we're not quite there. So we do have to do a little bit of thinking, a little bit of arithmetic to crack this one. Now, one thing I want you to remember, one thing we've mentioned earlier in the semester that we're going to carry forward here is the area of this shaded region, which is the whole distribution. That area is exactly 1. That's why you might remember this, right? If I took this and I slid W in, I made it smaller width, it would be a taller height. If I had a longer width, it would be a shorter height. And that's because the shorter the range of outcomes, the more likely you are to get a specific outcome. The more outcomes you have, the less likely you are to get a specific outcome. But there's my width right there for the whole rectangle. Let's do a little bit of math, a little bit of arithmetic here. So my overall base width here is 350 seconds. And if I subtract away the part I don't want, which is 180, that gives me 170 seconds as different outcomes I could have, or the range of possible outcomes that are above 3 minutes. And if I divide that by the total width, I get 0.485. Now, the fun thing about rectangles, if you can call it fun, is to go from 3 up, that's 48.5%, 48.6% of the total length here. Well, wait a minute. Rectangles being rectangles, would that not also mean that the area of, let me change my z value here. There we go. Would that not mean now that the area of just this piece right here is also 48% or 48.6% of the overall area? And actually, it is. And so you can pull this up out of the textbook, and now that we have access to my lab, that will be freely available to you. You'll find some fancy formula for calculating that. But the short version is that's a way to do it. You just find the portion of the range that you're looking at, and that portion divided by the overall range is the probability of being in that region. And that's because you just take that number, multiply it by a constant, and you've got it. You've got your probability now. And so that's why we're able to say, you'll say we got 48.5. That's the probability of being above 3 minutes. And that's how we do it. So to recap here, we've got a uniform distribution from data where everything's kind of the same, but not entirely. And so we just drew a line, a nice little bar here that made everything the same. We drew a line that basically connected our dots or our graphs. And so now what we're going to want to do is repeat this process of making a nice curve to connect the dots on a binomial distribution, this curve. And that's what we're going to do now. I will see you up ahead.